Hello and welcome back to section 18. In this video we'll be going over example 3, which looks at using Euler's identity to convert our sinusoidal signals into exponential signals. We want to do this because exponential signals are much easier to integrate and differentiate, and will make it easier for us when we evaluate them in our first order circuits. So Euler found if I add those two green vectors up, because they are essentially vectors, cosine being in the real direction, sine being in the imaginary direction, then I will get e to the imaginary part of the angle. So normally you would use I, so you would get ei times whatever it is, so we would probably typically use some kind of a theta to represent angle. In this class, we're going to be using j to indicate imaginary numbers. And that is strictly to do with the fact that we have already reserved I for current, and we don't want to get confused. So anytime you see a j, it means imaginary numbers. I's are still going to be currents. Again, we don't want to get confused. So what this allows us to do is rewrite sinusoidals and cosines as exponentials. So let's jump over to the visualizer and see that in action. So example 3 asks us to write the function v of t equal 10 cosine 2 pi times 6t as an exponential function using the real or imaginary operators. And so those may look a little funny. What the heck are these? So let's get there. So let's start off with Euler's equation, or his identity here. So his identity looks something like a e to the j. Remember, j means imaginary. And so the diagram just showed j omega, but we want to expand it. So omega t plus phi. So this should look familiar from our sinusoidal form. So we still have our angular velocity, or our angular frequency, whatever you think of it as, and then our phase shift. So those terms are still in there. And this is our constant in front. And that is going to be equal to some a cosine omega t plus phi. So all of that information will be the same. And then plus j, again j for imaginary, a sine omega t plus phi. So as you notice, our sines have an imaginary term in front of them, our cosines do not. That is the main reason why you'll see almost every problem use a cosine function and not a sine function, because it's much easier to relate back to the real part of this instead of the imaginary part. So we call this the real part, and we call this the imaginary part because this has an imaginary term in front of it. These operators, so the real operator, so if I took my a, e to the j omega t plus phi and said just return the real part, then I would just get a cosine omega t plus phi. You can think of these operators kind of like absolute value operators. So they're going to modify what it returns. So instead of returning the entire thing, it just returns the real part of it. The imaginary operator does what you think it does. So again, if I say, oh, imaginary operator, act on ae to the j omega t plus phi, well then that is just going to return. So basically what happened is we would expand this thing out into this plus this, but only this has an imaginary term, so only this gets returned. And so we would just get a sine omega t plus phi. And there would not be an imaginary term because that was the marker for that. Okay, so let's take that knowledge and apply it to our example. So we have v of t equals 10 cosine 2 pi 6t. So let's just rewrite this real quick. Let's just simplify that. So v of t is equal to 10 cosine, so that's going to become 12 pi. So let's go ahead and simplify that. 12 pi t. And there's no phi here, there's no phase shift. So we have a cosine function, which means we just have the real part. So if I wanted to rewrite this as an exponential, I would say that this is 10 e to the j, and then we just repeat our omega t plus phi. So this is omega, so 12 pi, t, and then phi is 0, so I'll go ahead and put that in. So just to follow our form up here. Actually here. We're going to write this again, but let's just do it this way. So we take this, we want it to look like a e to the j omega t plus phi. So a is 10, e, j, omega is 12 pi, t and phi is 0. There's no phase shift because there's no phase shift inside of there. But this piece, oh sorry you couldn't see any of that, is going to return back. So if I broke this apart, it would bring back both of these. So I only want to put the real operator on it so that it's equal to the cosine. So we actually want to put a real operator on here. I know that kind of got squeezed. So let's rewrite that. Alright? So that's what it looks like. We now have an exponential function that we can then evaluate with a derivative really easily. If you have any questions, feel free to contact me.